went through policy iteration a little fast last time, so I wanted to say a few words about that again. Policy iteration is another way of solving an MDP. Instead of forming a value function and converging and then acting greedily, you don't even bother computing the real value function. You compute a value function that's relative to the current policy you're thinking about. So I talked about this. I said you could do some matrix math to solve these because this was just simultaneous equations. But I want to give an alternative to that. Does everyone remember basic policy iteration? Right? You've got a policy. You compute the value of every state, assuming you follow that policy, and then given that you compute a new policy. And this will converge, and it will in fact converge to the optimal policy, and it's often way faster than value iteration, which is really nice. Here's where we see that they're just simultaneous linear equations. The value of S, given that I'm acting according to pi, is the immediate reward plus the discounted future reward. And the future reward is really easy. There's no there's no max, because I know exactly what action I'm going to do. If I'm acting according to policy pi, I do whatever pi tells me to do in S. So instead of some A here that we're maximizing over, there's just one, there's just whatever the action is. So this is linear. This is just a sum of these multiplied terms. Now it's a really long sum for every S prime we could ever transition to. But still, it's just a linear equation. There are a whole bunch of them. You can do linear programming, which is cubic in the number of states. Or if you have a big problem with like 1,000,000 states, and then n cubed is a really unhappy number, you can just do value iteration a few times. And it's simplified value iteration. You're not doing the max here anymore. Here, ordinarily, we'd take the max. In the Bellman equation, there'd be a max here, but we don't have to because we know, again, what action we're taking. So you just do simplified value iterations a few times. Now we've updated U, and that might be enough to let us choose a better policy without even converging. So there's value iteration, there's policy iteration. Policy iteration includes this policy evaluation step where you compute the value of each state if you act according to the policy. And one way of doing that is using simplified value iteration. So this phrase value iteration comes up again inside in the inner loop of policy iteration. I just didn't want you to get confused. All right? So that's policy iteration. Now there's one more thing I want to talk about, but I seem to have not re-LaTeXed my slides recently enough. Oh, here, it's right here. This is the last thing I'm going to say about MDPs. This is my all-time favorite MDP algorithm. Nathan.
I still have a question on policy.
That's fine.
Okay.
That's fine. I won't hold it against you until I'm grading your project.
It's a different slide. Is there more than one policy?
Could be.
Oh, that's okay. Given you calculate policy by one step, how do you? Is that calculated?
What do I mean by one step look ahead?
No, I mean like.
Given you. So you have you.
Yeah.
Now, for every state, compute the best action to take.
Okay, so
Using that old pi of s equals argmax of the expected value for each action.
So this is calculating pi star, basically.
Well, it's calculating a new pi. It's not guaranteed to be star because u isn't star. U is just u pi.
So
If pi sucks, then these u's will suck.
okay.
But amazingly, according to some proof that I don't even know and can't therefore give you in class, you're guaranteed that it's just life's going to get better. That the policy you'll get after doing this is going to be either better than the policy you had before, or you already had the optimal policy, which to me is just an amazing thought. It just gives me hope for my own life, that we can start out acting randomly, learn the value of things, adjust our policy, and get better and better until we're optimal. It's so amazing that that would be true, but it is. Someone was smiling when he made this universe.
Is this the one that the grads have to do?
Yeah, exactly. Any other questions about policy iteration? Okay, last MDP algorithm, I totally promise you, RTDP, real-time dynamic programming. Oh, I love this algorithm. Why do I love it so much? Because it's awesome in two respects. So value iteration I hate because you update the value for every state, even the states that suck. Policy iteration is nice because it's faster than value iteration, but still you're computing the policy for all states all the time, which is kind of pointless because some of them you're going to reach, some of them have a very low probability of getting reached, and some of them have just because of the transition function, like it's very unlikely that all the air in this room would suddenly go to the corner. Like apparently that is possible. People tell me that air molecules move randomly, so therefore there is a non-zero chance that all the air in this room will like end up there like for the next hour and we'll all die. Or we'll all rush to that corner and be trying to breathe it. But we're not all going to fit, so only some of us are going to make it. So there's that could happen. Like that's a reachable state in the MDP of our lives. Do I think it's worth planning for? No, because T, the transition function, tells me that's super low probability. Not only do I dislike policy iteration and evaluation because they don't pay attention to the T's, but they don't even pay attention to the policy. It could be there's some state that's very reachable according to some action that I will never do, right? Like I've never been in the UNH lockup. I've looked in the window. I was in that building. I don't even remember why. But there is we have a jail on campus. It's got like shackles and it's like very 19th century. There's some place where they put the drunk kids that they round up on Saturday night. Thank God. Anyway, so there's some action that we could each take that would end us up there. But we're not going to take it. So do I need to really speak for yourself? Yeah. Is it worth my calculating the U for that state? Exactly what is the future expected reward from being in shackles in Santos' house, or whatever the thing's called, Janetto's house? I don't care, actually, because I'm not planning on ending up there. I'm not going to do those actions. So RTDP is great because it pays attention to the transition function and it pays attention to what your policy is starting to look like. Furthermore, it's got a third wonderful feature. It's an anytime algorithm, just like value iteration. You run it for a while, you get a policy. You run it more, you get a better policy. You run it a lot, I think it's guaranteed to converge in the end. But actually, if you want to run to convergence, it's actually slower than value iteration. But it's great for finding a good policy quickly. The whole reason I hate value iteration is it updates everything. So which states do we update? Well, so start off, initialize U to be totally optimistic everywhere. I see this as a motto for life. Initialize your U to an upper bound. This is why I give you the upper bound in the initialization function, so that if you want to implement RTDP, you can. And also Q-learning. Initialize U to some upper bound. Now, start in the start state, follow the greedy policy. And every state you traverse, do a Bellman update. Remember, this is for a known MDP. This is I'm doing the topics all out of order today, for which I apologize. But this is not for reinforcement learning. This is assuming you know the MDP. So you actually simulate living the MDP. It's like you're pretending you're doing reinforcement learning, except that you actually know the model. But you simulate. You start at the start state, and you follow the greedy policy for a while, and you update every state you touch. So therefore, it's going to be the states that are probable according to the transition function and the states that your policy will actually visit. If you do some boneheaded thing and you're like, oh, wait, going and, I don't know, being a jerk to somebody is a great thing to do, and you do it, then you'll immediately update, right? You'll get the negative reward, you'll immediately update, and now you'll know. And you won't do it again. Next time you come back to that state, another action is going to have higher utility. After you've tried every action once, you'll have a decent idea what's going on, and pretty soon you'll be following a pretty decent policy. So this is this is my all-time favorite MDP algorithm. It's just so simple. Just follow the greedy policy and update every state you touch. That's the update policy. So it's better than prioritized sweeping, because prioritized sweeping just updates the things that have big updates, even if you're never going to reach them. Questions about RTDP? Yeah.
The greedy policy is the policy that.
There's a problem though with ADP. Speaking of the greedy algorithm, we can think about it even just here when we're doing value iteration. ADP with value iteration. And value iteration is going to converge to optimal if you know the model, but you don't know the model. So what could happen if you're greedy? All right, we're going to take, this is the thing you were just trying to get to, Nathan, where you take the action that is maximizing your current understanding of the reward.
Okay.
You would get the one-step look ahead. All right, we're looking one transition ahead, and we're taking the action that maximizes our reward on the assumption that U is correct. But we don't really know the model perfectly. We don't have tons of experience in the world. Yeah. So what kind of problems can this lead to? Frank.
You find something that looks okay and you don't explore anything.
Exactly. Today's lecture is about life. I already told you it's good to start off. I already told you it was good to start off initializing your upper bound to maximum reward. The other lesson for today is don't be greedy. So you take a computer science class, you love it. You're like, oh wow, high reward. I'll do that action again. You take another CS class, wow, this is great. I found the major for me. It's fabulous. Take it on. Pretty soon you're like a senior. You're like, oh shit, I got to take some liberal art electives. Damn them. Why do they make me take poetry? Because you haven't tried taking a poetry class yet. Maybe it's got fabulous reward and you've never tried it. Right? So then you try it and you're like, oh, I love it. It's even better than computer science. I know. I like poetry only in small amounts myself. But
be fun.
Funny?
Yes.
No, they don't.
It helps.
They have to be beautiful. Beauty helps. Beauty goes a long way. So premature commitment. So this is the fundamental tension in reinforcement learning, aka life. Right? You were in a state, you took an action, things worked out great. You're in that state again. Do you take the thing you never tried? Could be bad. Could be even better than the thing you already did try. I love my father, but when he goes to a restaurant, he pretty much orders the same thing he ordered last time. Yeah. So you are making that trade-off in a certain way. And the question in reinforcement learning is, what's the optimal way to make that trade-off? So it's called the exploration versus exploitation problem. And it's not exploitation as in Foxconn. It's exploitation as in you know something, you have knowledge. I know this is good. I'm going to exploit my knowledge that that's great. Versus exploration. Let's try some other things and seeing if they're any good. There are a bunch of ways of trying to resolve this dilemma. And most of them involve a little bit more math than we've seen so far. So we're not going to talk about them, but they'd make great final projects. Sorry. The book offers this solution, very simple hack, which is to try everything at least k times. That's their version of resolving this. So you'll never completely ignore something because you never tried it. You always try something at least k times. This is the way they formulate it. They say that the utility of something is the immediate reward plus the expected future reward. The expected future reward, this is actually f of expected reward and the number of times you have done A in S. And this function is totally awesome if n is less than k. Otherwise, it's the normal expected reward. All right, so this ensures that whatever the action A is, if you haven't done it at least k times, it's like, oh, maximum reward, like total best high ever. But then once you've done it k times, it's like back to reality. So that's one way of getting around. This is a cheap hack. It's one way of getting around this exploitation problem. You won't just do exactly the same thing you did before. You'll at least try everything a few times. I have that problem in restaurants where there's a dish I really want to like and I order it and it sucks and I'm like, oh, but I really wanted to like it. Maybe it was just a bad night. And so I go and I order it again and it still sucks. And I'm like, but. So that's the question of how big K should be.
Is there a way to get around it which takes into account the fact that you can die?
No, we've been talking about the infinite discounted reward setting, so you never die. Finite horizons are a little trickier. Die. Well, okay. So this is just a way of making sure you have a little bit of evidence everywhere so that you try stuff. When we were doing deterministic planning, how did we deal with this problem? How did we encourage the agent to consider possible future avenues? And yeah, we had a heuristic function, exactly. So if you have a heuristic and you know that certain things are good and certain things are bad, you can initialize U with the heuristic function and do value iteration. Yeah. Sorry?
Like when your food kills you.
When your food?
He said die and you were talking about food, so I'm like...
Food, yeah. I got sick from eating at a very fancy restaurant once. I was really upset. No, I would actually go back to that restaurant. It was pretty cool, and people say it's great. So I think it was just bad, one-off random occurrence. Yeah. I'm getting hungry. So exploration versus there are all kinds of super elegant algorithms for dealing with this, but they're a little more complicated than I want to get into here. So exploration versus exploitation. The word bandits is here because the mathematical framework for studying the exploration versus exploitation problem is called the one-armed bandit problem, or the K-armed bandit problem. I shouldn't use K. Let's just call it the multi-armed bandit problem. You have a bunch of slot machines, and every time you pull an arm, you get a reward. So the question is, what action do you take next? Yeah, but which one? So if you pull an arm and a lot of money comes out, you might be tempted to think, oh, I'll just keep pulling that arm. But how do you know that this other machine isn't going to give you a lot of money? So you want to go try that arm. Well, it didn't give us much money. Well, is that just random happenstance? How many times do I pull before I give up? So if you make some assumptions about what probability distributions the rewards follow, you can actually prove things about how many times you should try an arm before pulling just the best one, the one with the best expected value given your experience so far. There's some beautiful mathematical results.
So K is the number of times that we try an action. Is that from what that says?
Yeah, under this hack.
Yeah. So is there a way that you can have K grow as the program, or as it continues over a long period of time?
Intermix exploration.
Yeah.
Yeah, another thing you can do I have this on the slide? Oh, no, I don't. Another thing you can do is try a random action with a certain probability. Like 90% of the time you take the thing that looks best, and 10% of the time you do something random. And that way, if there's something good, eventually you'll try it, and it will be great, and now you'll take that one. So there are things like that you can do. There's a whole literature about this problem. It's really fun. Very fun. Yeah. It turns out when you get hired as a professor at UNH, you can make the library buy you a book. Any book, but only one. And the book I chose to make the library purchase is a book on bandit problems. Because it's just so awesome.
Not coincidence that one is on the page.